Hello, I will talk about complex base numeral systems, which are standard numeral systems, but using base, which is a complex number. So here we can draw on a notebook this kind of representation, which create kind of fractal. So for base being complex number, imaginary number j minus 1, and looking at this set, we can represent with this integer part of the expansion. We get the following subsets denoted with grayness here. You can just draw on a notebook. So yes, so I have realized it in some high school. Then written two master theses about it. Then a year later, it also inspired me to a symmetric numeral system. So the materials can be found in the links here with details. Okay, so we have some positional numeral system that we would like to represent all numbers x as this kind of sum of power series, with digits being in some discrete set. So digits we use from 0, 1 to up to some n minus 1. So we denote n as the number of digits. So there was binary, so 0, 1 at the previous, and here we can use general digits. And we have this kind of expansion, representation, and the question is if you can represent all the numbers in preferably in a unique way. However, the uniqueness is not easy to achieve, because also in one dimension we have these examples that zeros and all ones in binary system is the same as 1 and all zeros. So you can have a number of these kind of examples with finite representation. In 2 dimensions, it's even worse. So we don't have just countable number, but rather of non-zero Lebesgue measure. So here at the pictures, the points of the boundary have 2 representations. So one representation is while going from 1 this fractal, this fractional part, can achieve, and the other representation is from the other fractal. At the points at the crossing of the tree can be obtained in 3 ways by using representation from one of the 3 regions. Okay, so we choose some base, we choose some n. So usually this base is the same as n, but here it's more complicated. We talk about the details of this z, of choosing this z. Then we can define this integer and fractional part. So integer part are the numbers we can get with only this non-negative position, so before the comma, and the fractional part what we can get after the comma. So finally, with adding these 2 sets as the set of all sums, we should get the entire plane here. So the integer part, is a bit different than fractional part. So integer part is discrete, is not bounded, and the fractional part should be a set, should be some continuous set, bounded, compact. So for example, for standard binary system, we have this fractional part is 0, 1 range. So what we can get with all numbers with 0 and any digits after the comma. So it satisfies this kind of self-similarity relation, that if we multiply by 2, then we get all the numbers which has 0 or 1 at the first digit, comma, and any digits after the comma. So this multiplying by 2 by the base of this system, we get 2 copies, union of 2 copies shifted by this 1, by this choice of the first digit before the comma. For the integer part, we have now discrete lattice. So we can get any natural numbers for binary system, which can be split into even and odd numbers. One just multiplied by 2, and the second the same, but also shifted by 1 by this first digit. Okay, so these 2 parts, this integer and fractional part, satisfy this self-similarity relations, which might look similar, but they are very different. One leads to this fractal, this iterated functional system, the fractional part, and the other leads to lattice. So there are look similar, but they are different because one is contracting and the other is not. Okay, so having this iterated functional system property, this self-similarity relation, it uniquely defines a set if only we know that K is compact and non-empty. So in this case, we can using this self-similarity relation multiple times, we get this kind of formula, and finally in the limit we see that this Fz kinds of forgets about the exact structure, and we get this unique compact set in unique way. So having this theorem that we have this unique set defined this way, we can for example find and prove existence of symmetric center of symmetry. So here is for set K, x0 is center of symmetry if K minus x0 equals x0 minus K. Yeah, so this is kind of definition of center of symmetry. So we need to look at this set to x0 minus K, and choose x0 such that this set satisfies this self-similarity relation. So expanding this the self-similarity relation for K, as here, we get that x0 needs to be this value to have, so that 2x0 minus K satisfies this self-similarity relation, what allows to conclude that the set is our fractal the same. So we have just found analytical formula for the center of symmetry of this fractal. Okay, so there is this big question how to choose the base, the Z. So for standard numeral systems in 1D, we just take the base equals the n, the number of digits we are using. In 2 dimensions, it's more difficult. So one question is simple. So what is the modulo of Z? So here we will see that modulus of Z should be square root of n, and generally higher dimension should be the dimensions root of n. So because of the measure analysis, we can get requirement for absolute value of this base. However, for argument part of this complex number, it's much more difficult. So I will discuss it later. So first of all, we would like it to be surjective, then such a representation. So with this fj plus fz plus iz, so it is all the numbers we can represent with both the fractional and integer part, and so this is a set of pairs of sums. So the question is if we can get the entire complex plane here. So this is this surjectiveness, and we have this injectiveness, but not complete. We have these points with 2 or more representations. So we would like that its measure, second Lebesgue measure, is 0, or its Hausdorff dimension is lower than 2. We will find the Hausdorff dimension later analytically for this kind of sets. So to make such pair, this n number of digits and z base proper as surjective and pseudo-injective, we need that this fractional part has non-zero second Lebesgue measure, because otherwise we have only countable number of copies by this adding this integer part. So otherwise it couldn't be surjective. Yes. Also, such 2 fractional parts shifted by 1. So it means by changing this one digit in the front before the comma, the intersection cannot have larger measure than 0 Lebesgue measure. And so finally, from these 2, we get this relation that this n has to be a modulo of z squared. So this is necessary condition for this absolute value of this base z. So the last one we can get from this, that that n times second measure of fz, using the self-similarity relation, we get so fz is this union of this all the shifts. So we need the relation that this n has to be module z to power dimension here. So here we use dimension 2. I will also mention the end dimension 3. So analogy it will be the third power of z. So then there remains this difficult question: how to find the argument of z. So this is really tough. So here is so we know that the z should be of this form: square root of n times some argument, complex argument. So first of all, taking this complex conjugate of z, we get just complex conjugate of the entire set, what is easy to check. So in fact, it is sufficient to focus on this one quarter of the full angle. So for this one quarter of full angle, here is a numerically found Hausdorff dimension of such set. So to get surjectiveness, this Hausdorff dimension has to be 2. So we need to have two-dimensional set to get this surjectiveness we would like to have. So we see that here we have the for 1/2 we get something like that the even and odd coordinates of this representation. One represents the real part, second of the imaginary part. We get this kind of the fractional part is this kind of rectangle, just, yes. And so for the limit of this angle to 1, this complex number becomes a real number. So finally we get just the fractal becomes flat. So here is this limit, where in this limit finally we get one-dimensional structure. So in the limit, this plot should get down to dimension 1. How's the dimension 1 at the limit? But we have also we see also these two maxima, which is the interesting cases. So in these two maximas we can really expect that the two-dimensional the subjectiveness that we indeed cover entire complex plane with this kind of representation. And here we have this rotation of this. So this plot, but looking at these fractals, this fz part we would get for various angles. So we can see that here is this rectangle. We rotate. So every such smaller fractal is also rotating. And finally, here we see again we no longer have the holes, and so it has indeed. So it is in one case, it's called tamed wind dragon in this fractal nomenclature, which indeed leads to covering of the entire complex plane. And here is another. Here is standard twin dragon fractal. So these are these two maxima. Here is the rectangle. Here is this tamed twin dragon. Here is the twin dragon. So here is for n equal 2. We have 2 digits. For n equal 3, we have one more. So so we have this kind of analog to this tamed twin dragon, the twin dragon, and some additional one, which is kind of the most strange of them all, and n equal 4, and so on. So here is for n equal 10 and 12 and 13 the Hausdorff dimension numerically found. So we can see that this number of these cases when we indeed should get this full covering, this surjectiveness, so the representation of practically all points on the plane for this discrete set of cases. So I have some classification of these discrete sets I will talk about. But I wasn't able to prove that it's complete classification. That there are no cases which cannot be described this way. Okay, so let's look at this classification of this maxima, which hopefully all which are hopefully all cases with complete covering of this 2D plane, complex plane. Okay, so I call them periodic cases. So the criterion used is very simple, and numerically at least can some to work. I wasn't able to prove that it's complete classification, but the simple criterion is that z square. So we have to use this z square as the for the second digit. So the question is if it fits the lattice made from z and from the previous digit. So if it fits the lattice, so it means that z square belongs to this set, this lattice. Then our fractal is kind of this periodic lattice. So this is kind of natural intuition for which we can get complete classification. However, we don't know if there are no other cases of this representation over the whole complex plane, which does not satisfy this classification. So from this rule, you can have this small d, and finally this is this capital D for integer. So we can find that the z has to be of this form. For d, capital D being integer and not too large, not to make this square root positive of positive value. So for n equal 2 we have this rectangle and two fractals on both sizes of the sign. For 3 we have 3 as in the plots, yes. So here are this plot for n equal 2, n equal 3. Okay, so the sign of this capital D controls kind of shift, and it turns out that the positive signs lead to this kind of situation. So here we have two colors. So it means that the zero is at the boundary of such fractal. So it means that using this, increasing this fractal by adding the following digits before the comma, we will scale it, but still there will be some hole. There will be missing a second fractal. So we can to fill the entire plane here for these three cases. We need here two fractals, so we need the original and the shifted one. In the paper it is derived this classification, at least for periodic cases. And for this case, this most strange case, so this is this one. We need three fractals. So to cover the entire plane, here we need three fractals. However, using this d, capital D, as negative, we get one fractal. So the question is if 0 is in the center of such fractal or at the boundary. So if it is at the boundary, we need two or more copies. So in the paper it's described in details. Okay, to practically work on such fractals, such representations. So in the papers I have used this kind of notation that we have this bracket and there is z, so it should be interpreted as 1 minus d times z plus n times z square and so on. So we read kind of from the right to the left. No, it should be the opposite, but it was chosen this way. And so what is crucial that this periodicity says that z square equals dz minus n. So it can be written in this notation as this triple equals 0, and we can shift this triple toward the left by multiplying it by z, and it will be still 0. So this rule asks for simplifying the relation there. For example, for n equal 3, d equal 3, we have z is this number. So we have these three fractals. So we can have a problem as here that the zero is at the boundary, and in fact not always we can find the representation. And the problem is such that sometimes this kind of reduction procedure will never end, because we get in a cycle. So here we can have this problem, and we need this three shifted fractals to completely cover the plane. Okay, so for example, if you would like to translate this number in standard coordinates to this complex base numeral systems, we write that it's this kind of notation, which is not nice because it uses large digits. Why we would only like to use digits from 0 to n-1, so from 0 to 2. So what we can do? We can subtract or add this 0. Yes, we know that this is 0, so we can subtract it. And to get so finally we get this notation. So we can see that it's 0 plus z squared plus z to the power 3 by using a few this kind of reductions. Also we can go the other way by using this kind of reductions, and it also allows us to find some general formulas how to represent large powers, not only second power but large power in this smaller powers and so on. So it allows, so we can practically work with this complex base representation, for example, to work on pictures, and so I will also show some example of working with pictures for some data compression applications, for example. Okay, so there is some proof that we have these two cases with when we need three fractals. Here you have one, but now the colors only represent the first digit. Okay, so here is this example of application. So data compression, loss image compression is usually based on Fourier transform, but there are also the wavelet approaches. So, for example, this Haar wavelet is just replacing values with differences between left and right mean value over some region. So we could change it into this into values being differences between mean value over this fractal minus minus over this fractal, and so on. So then we can imagine that this fractal is split in half, and again new parameter, the high level parameter gives difference between mean of this quarter and this quarter, and so on. So this is kind of similar to Haar wavelets, but using this kind of fractals instead of just squares or rectangles. So why fractals could be more interesting? Because from one side the boundaries are less obvious. So this kind of artifact should be less clear for the person who is seeing such pictures. So to have less clear boundary artifacts. Another nice property is that here you have this hexagonal structure. So we could see that there was this hexagonal structure of these regions. So in hexagonal structures we can better exploit local neighbors to get some information about this new region. So it might be better for prediction. Also here are some examples of picture you can generate with this simple library. That instead of some region of this fractal-like region, we have one color. So if we cut all the digits describing information for lower levels, we would get this kind of artifacts, boundary artifacts. They are relatively large, but I don't know. Okay, so the following part is this convex hull of this kind of fractal. So the details are in the paper, but generally these are some ideas how to replace this self-similarity relation with we can use it self-similarity relation to to get self-similarity relation for some functions describing some properties of given fractal. So, for example, such function can be this H function, which saying so we try to put some half planes bounding the fractal from different directions, and the position of such half plane supporting from this direction can be defined by given function. So for every direction D, we say how far is the supporting plane in this direction. So for this kind of function, width function. So what is the width of the fractal in given direction? We can get simple self-similarity relation. So we can find this function from this self-similarity relation, and it defines not entire fractal, but only the convex hull of the fractal, of the fractional part here. So we can translate it with some more intuitive this direction function that what is the distance in given position, not what is the position of this supporting plane, but what is the distance. We can translate between them with this kind of optimization. No, it's not very simple, but can be fun. So, but the most important is that we can find this width function, this H function, these positions of the supporting plane from the self-similarity relation. We get this kind of relatively simple formula, which allows to get the convex function, the convex hull function, find its area, its circumference, and also approximate. So, for example, we can get this function which says if given point is in distance L from the fractal. And it can be done by testing this kind of these bounding half planes found here and going some inside the recurrence, and so we can. It's a difficult question. If the point is in some distance from the fractal, and here it can be automatized in a relatively simple way. So here we represent the boundary, the convex hull with something with the dispositions of the supporting plane. So it's not exactly so. So in fact we are representing this way the set with these circles around. But if going in the recurrence, so dividing this fractal into some subfractals, then we can improve this representation and this example of procedure using this recurrence. Okay, so for these simple fractals, we can get this simple formula for this width function. So for every direction, we have this position of this supporting plane. So it supports at least one point, and if we would turn this rotation, this supporting plane has this minima, like here. So here is one minimum of this supporting distance. If you would rotate a bit, this distance would increase. And analyzing this minima, so here it is. So here are some such 2 points, some 2 angles. And analyzing this bouncing of this minimal distance, we can decompose this convex hull of the fractal into such triangles. We can and what allows to calculate. So we split such convex hull into triangles, which allows to find the length of the boundary or the area. We have analytical formula just as a series. And also it's interesting that we get some nice inequality. So we know that that for given area, the shortest circumference length is for circles. So we get this kind of inequalities. I haven't found this kind of inequalities in literature. Here they can be found analytically by this analysis of this convex hull. And here is some example of the different n, this number of digits, and these periodic cases. So only two. So here is this rectangle. Here is time twin dragon and twin dragon, and so on. So okay, so here is if you divide the so how close to the convex hull is to the volume of the fractal. So for a rectangle, the convex hull is the fractal. So we have one, but for further. So here we can see that the fractal has only some percentage of the convex hull. That we can find that this percentage is this 1,166. So 1 and 2/3. So the convex hull is larger by this proportion here. So we can find analytically because the area of the convex hull can be found by this size of the lattice, the volume of the lattice. So we can find these interesting relations here. Okay, so some another discussed function we could try to analyze. I have tried to do it, but didn't lead to anything interesting. But we can, for example, analyze this kind of functions. That what is the measure of intersection of two fractals shifted by some x as function of x. We could get this function by analyzing this self-similarity relation, and you get this kind of density plots. It's interesting, but I wasn't able to get anything from here. Okay, so the next part is finding finding the exact construction of the boundary of this fractal. So here is some iterated process of creating this boundary by some this kind of rules. So my first thesis I have found it for this twin dragon, and the second for general fractals of this entire table of n periodic and the periodic cases. So we can find this kind of recurrence relation, which can be translated into some matrix. How many given types of edges will be translated into various types of edges in the next set, and looking at the dominant eigenvalue of this matrix, and from its logarithm we get Hausdorff dimension of this boundary of this fractal. From its eigenvector we could get the proportions of different types of edges in the asymptotic limit. So we can tell a lot from this kind of analysis about this boundary of this fractal. Here are the proportions, the dominant eigenvector. Okay, so and in the second thesis a year later I have generalized it into general these periodic cases. So in general case we have this central fractal and its neighbors. It has always this hexagonal structure, 6 neighbors, and after this using Y magnification, this multiplication by Z, going to this self-similarity relation, the central fractal becomes, let's say, 2 copies or more, and so on for the remaining. And each such original step, and so we need to remember from which we go here and to which we go, and each of them changes into some sequence of steps in this magnification. So we can get these general recurrence relations like here, but for any cases. And finally, here are again we can find these matrices of transitions, and finally from this logarithm of the dominant eigenvalue we get Hausdorff dimension, and this is the analytical formulas for Hausdorff dimensions of these various fractals. So it seems it was completely unknown, and it was found in my paper 2005. And there is nice there are nice demonstrations. So here are simulators, and for example this construction of the boundary of this kind of fractals. You can find the recurrence, the matrix, the middle eigenvector, and see how the succeeding steps look like. Okay, and this is the final slide. So what was happening in higher dimensions? We have went from the standard 1 dimension to 2 dimension. And so in higher dimensions, we analogously need that this r, this length of this base is root these dimensions, root of the n number of digits, instead of some bases as some length and some rotation. Here we have general rotation, some orthogonal metrics. And for these periods, so it becomes, of course, obviously even more complicated. But for these periodic cases, we can find some rules. And so here is this reduction to 0, and it can be found. There is also a simulator for this. Oh yeah, here is a simulator for this kind of case. So it can be studied, but it's much more difficult. You could also find this recurrence for the boundary of this kind of fractals, but it is becoming very, very complex. Oh, thank you.